Okay, thank you very much for the introduction. Thank you also to the organisers for inviting me to come here. It's always a great pleasure to come to France, especially the south of France that I don't get to often enough. A nice change from the weather in England at the moment, that's for sure. So here's my talk title. It's probably the longest title I've ever had in a talk, and I'm about to make it longer because it says there, a test for local white noise components. It's also, there's a slight variation that I might mention a bit later, which is really a test for local white noise as well. But this particular talk, the way it's framed, is local white noise components. And it's joint with Idris Eckley, who's at Lancaster. So just give you a quick outline of the talk, a little introduction. I'm going to talk a bit about the model setup and background, because I wasn't quite sure exactly who knew anything about locally stationary wavelet processes, although there's people who know more than me in the audience. I'm also going to explain how they behave when you subsample the locally stationary wavelets, and how that can cause aliasing. Although, of course, it's not the only way that aliasing can crop up in time series analysis. There are many different ways in which it can occur. Same basic idea, but the details are different in slightly different places. And as I said, explain how locally stationary series with the wavelets behave under dyadic subsampling. And then I'm going to talk about detecting white noise components and why, in this particular model, in this particular way, you can detect, if you like, a lack of aliasing in time series. And this talk, where does it come from? Well, it comes from because I'm very interested in sampling rate problems. So, you know, are we sampling too fast? Are we sampling too slow? In other work, I'm interested in knowing if you sample at one rate, is it worth going to a faster rate and getting the right information from that? Or if you've got information at one rate, do you want to slow down? And probably you guys talk about this all the time, right? Sample rate is really important. And, you know, you don't need me to tell you how important that this is, but I do a lot of work with a lot of applied groups, the Office of National Statistics in the UK, for example. And although they talk a lot about a lot of things in time series analysis, sample rate is not something that's right at the front of their minds. So that's why, especially when I'm talking to those guys, I often refer to it as the elephant in the room. You talk about everything else apart from the sample rate, okay? So this is just a nice little cartoon with a very worried-looking elephant. And I was thinking about a joke with white and noise and elephants, but it didn't really work, so I think I'm going to leave that out for now. Okay, now I'm going to very quickly go through the model setup that I use here. I'm well aware of the fact that it's a specific model setup, and I'm also very well aware of the fact that the reason why what I'm talking about works is because it is in this framework. Okay, so if you put it into a different framework with a different basis, then you don't necessarily get the same thing. However, it is still, I think, of interest. And the reason I'm not going to go into huge detail and go quite quickly is a lot of what I'm talking about here is very well known by now. But there may be some people who won't know what I'm talking about unless I say a few words. So let x of t be a time series of interest. So t is discrete time here. And I'm going to suppose x of t is modeled by a locally stationary wavelet process, which has an evolutionary wavelet spectrum Sj of z. Z is this rescale time in 0, 1 that Rainer knows all about. And the model I've got for my time series is here. X of t is a double sum over scales j and locations k of 3 bits in each term. So amplitudes wjk, wavelets psi j k minus t, and psi jk. And so the psi jk is a set of uncorrelated random variables with mean 0 and variance 1. And I should also say the other co-inventor of this person is the guy I'm lasering over there, Rainer von Sachs. What are the other components? So the psi jk are non-decimated. Don't worry about what they are if you don't know. Discrete wavelets, and we'll show a picture of those in a second. And the wjk are amplitudes. So this is essentially a wavelet-based version of the usual Cramér representation for time series. So you have randomness, oscillation, and amplitudes, and you add them all up, and you get a model for a stochastic process. And the process is, if you like, controlled by the timescale spectrum Sj of z. Z is this rescale time, so if you like, z is equal to t divided by capital T. And the evolutionary wavelet spectrum Sj of z, or k over t, is approximately equal to the square of the amplitudes. So if you like, this plays the role of the A of omega in a Fourier representation, the amplitude there. The smoothness of Sj of z as a function of z controls the degree of non-stationarity. And if you have Sj of z is equal to S of j, in other words, not depending on z, then you have a stationary representation for a time series. Okay. So just as just as an example, here are some discrete wavelets, very, very simple. So just 1 minus 1, 1, 1 minus 1 minus 1. So wavelets of increasing scale in the time direction, and they're getting smaller and smaller in the vertical direction. So they provide the oscillation in this model. There's a picture of those, and you can see, if you like, kind of the real Haar wavelet underlying this. Here's a picture of an evolutionary wavelet spectrum for a particular process. And I wanted to show you this just to get the idea if we have a time scale spectrum. And what it's going to do is operate at the finest scale for a quarter of the process, the next finest scale for the next quarter, etc., etc. And then if we take that spectrum, we multiply through by the amplitudes, add some randomness in, we get a realization which could be that. Okay, and you can see what's going on here. Here you've got that fine scale, next finest scale, next finest scale, next finest scale behavior there. So that's a concatenated Haar realization. That's a non-stationary time series realization there. Just a few other things that we'll mention along the way, a few other concepts, very simple. Don't worry too much about the details. Again, capital psi is the autocorrelation function of the discrete wavelets, and A is the inner product operator of the autocorrelation wavelets. So just take two autocorrelation wavelets and then look at their inner products at different scales. Okay, so there's just some things we will mention later on in case you're wondering what they are. Okay, I've talked about synthesis. If you've got a model, you've got randomness and spectrum. What if you now get some data and you think it might be a locally stationary wavelet and you want to estimate the quantities there? Okay, how can you do that? Well, given data x of t, we can compute something called the raw wavelet periodogram, which is I, is the raw wavelet periodogram. It's the square of djk squared. And what are the djk's? That is just the inner product of x of t with the non-decimated wavelet. So it's completely analogous to the usual Fourier way of doing things. Okay, if you want to look at the periodogram, you take the Fourier transform, you look at the squared absolute value. It's the same here, except we've replaced Fourier by wavelets. And what you can show, was shown, is, for example, the expectation of the raw wavelet periodogram is equal to this quantity here. So it's not like the regular expectation of the periodogram. What you get here is a blurred version of the wavelet spectrum. But it turns out that this is invertible, so you can get hold of an estimate of S by some a to the minus 1 applied to I. Okay. All right. So that's kind of the background. What next? Well, one thing I wanted to just show you is a useful example, but it also comes up later in the talk. What happens if you start off with x of t being white noise, zero mean with variance of sigma squared? Well, not surprisingly, the expectation of the wavelet coefficients is equal to 0, and the expectation of the raw wavelet periodogram in this case, that's just the variance of the djk, because remember the periodogram was the square of those things. And if you work it through, you get a constant. Okay? What does that mean? It means that if you look at the wavelet periodogram or a smoothed wavelet periodogram, an estimator of the ijk thing, and you get a constant quantity at each level, yes, in particular it's a constant function of j, the scale that you're looking at, then that could have come from white noise. Okay, and that's going to be of interest later. And the reason being that the wavelets that we're using will have norm 1 for all scales j. Okay, now let's move over to the kind of topic of the talk, which is aliasing. And again, almost everyone here, I think, will know what I'm talking about. I just wanted to just put one slide of introduction, so this is not meant to be new. So I have a time series, x of t again. And then we have the usual story. If you have integer samples, then you can define the Nyquist frequency. And using the particular normalization that we're going to use, that Nyquist frequency is pi. And then you get the usual things that actually if you sample 2 times slower, so you sample at 2t, then the highest frequency that you can observe halves. Okay, so pi over 2 becomes the Nyquist frequency. And what is aliasing? Well, aliasing occurs when there's power at frequencies exceeding the Nyquist frequency. So if you sampled at 2t, but there was frequency information in the original process higher than pi over 2, then you would get aliasing. I haven't got time to show it now, but I've got a nice video of the wagon wheel effect, but you can see that later if you want. It's basically a movie, you know, with car wheels going around and stuff like that. Anyway, but what's wrong with aliasing? Well, aliasing is where essentially you get this higher frequency information folding back and interfering with the lower frequency information, and there are several problems with it, which I think, as I said, certainly with my applied colleagues, they don't necessarily think about too much or worry about too much. It's certainly hard to know when it occurs. I'm not sure anyone really routinely tests for it. It can cause problems, I believe, for spectrum and covariance estimation. You get this phenomena of high frequency peaks moving into the lower bands, lower frequency peaks being distorted by higher ones. And I think has a strong influence or a possible influence on scientific understanding and modeling. And who knows, possibly forecasting as well. What can you do about it? Well, some things, depending on where you start from. Low-pass filtering. If you know quite a bit about your system, so for example, some physical experiments, you can do a low-pass filtering. Yeah? So if you have an analog signal coming in and you're going to be sampling it, well, you can use a low-pass filter to wipe out the frequencies that you know might cause aliasing, for example. Another thing is, well, just increase the sampling rate. You think there's high-frequency information there that you're missing out on, well, just increase the sampling rate. And you can sometimes do that, okay? Some systems can do that. However, if you're a big bureau of official statistics, suddenly going from quarterly to monthly to weekly samples is not a trivial task. But you can sometimes do that. However, in some situations, even when you can increase the sampling rate, there's a question of how much do you increase it, and you could go too high, for example. And also, there's a question, what about non-stationary series? What happens in that situation? And actually, in some ways, dealing with this issue with non-stationary series, I think, is easier than it is with the stationary situation. Yeah, because things can change with non-stationary, whereas they can't with stationary. Is there a test for aliasing? Well, yes. There's a paper in JASA in 1988 due to Hinich and Walensky, and it's based on the bispectrum. And it was published in JASA, and then like a whole wave of 3 or 4 papers in different journals criticized the idea, and then it was later clarified by another paper by Hinich and Messier. And it permits a kind of aliasing hypothesis test for stationary series. However, and as with ours, as I'll show you a little bit later, rejection of the null hypothesis in this situation can mean many things. It could mean that the series is not random, it's not stationary, or it could be aliased or not mixing. But the point is here that there's a confounding of effects. You can't really nail down what's going on. What about for locally stationary series? Well, as I said, a locally stationary series, as we all know, can change its spectrum over time. And if you have a fixed sampling rate, a locally stationary series could be sometimes aliased. Yeah, if the frequency content is really very, very high, higher than what the sampling rate can currently deal with, then you can get aliasing. And then later on, the highest frequency might be below the Nyquist rate, and you might not get aliasing. So aliasing can be a local phenomenon, which is quite an interesting thing. So we can ask, not only is a series aliased for a locally stationary series, but where is it aliased? Now, I'm going to set up a special way of looking at aliasing, and I realize it's not widely general, but it's something that you can do and have a look at. And what we're going to do is use subsampling to induce aliasing. So what I'm going to imagine is that we've got a locally stationary wavelet process operating at a very fast sampling rate. That's kind of in the background. And what you're seeing is something which has been subsampled from that. And that's what you observe. And the question is your sampling rate that you're actually looking at it enough to capture the information that's present in the fast sampled locally stationary wavelet process? And the reason why this is kind of special is that locally stationary wavelet processes behave nicely under dyadic subsampling. Okay, so be a little bit wary of what I'm telling you here, because it's kind of a special setup here. And the reason why the processes behave nicely is because wavelets behave nicely under the dyadic subsampling. And the processes, the LSW processes, become increasingly like white noise under subsampling. And we can see this by the following result. So if x of t is a locally stationary wavelet process with that spectrum, so that's the high frequency LSW, if you like, the kind of what's behind everything. And what we're going to observe are the y of t, which are the subsamples of x of t, but subsampled using this dyadic rate, so 2 to the r times t. Now, if you start with the x of t being this LSW with this spectrum, an interesting question is, what does this process y of t looks like? And what you can show is that y of t can be decomposed into a sum of two things, L of t and f of t. L of t is also LSW, like this, with a spectrum which I'll give you in the next slide. And f of t is a process which has zero mean and this autocovariance function. And what's interesting about this is that you have this delta zero Tor here. So it's not equal, but it's asymptotic. So this f of t is like asymptotic white noise. And in fact, if x of t was stationary, then you would have exactly white noise. Okay, so that's quite nice. So you have the LSW, high frequency, you subsample it to get y of t turns into something which is the sum of an asymptotic white noise process and an L of t, which is an LSW with the spectrum given by this formula here. Okay, so this is the spectrum of y of t, sorry, of L of t, Okay, and the scale there, L, is relative to the new series y of t. So, for example, if we just subsampled every two integers, so suppose r was equal to 1, then the spectrum of the L of t, hang on a minute, yes, looks like this. So you have two components. You have this component here, which looks a bit like, this was the original thing I showed a few slides ago. So this bit here looks very similar to that, not a lot of difference. But what's really interesting is you get this bit coming out here. Okay? And the key thing to notice about this bit is it doesn't depend on L. It doesn't depend on L. Okay? So what you get is, when you look at the spectrum of a subsample process where there's aliasing going on, you effectively get a blob of the same size at each scale, as well as some other stuff as well. Okay? So, what are the differences between the two spectrums if you do the subsampling? Well, after you've done subsampling, the highest original frequency spectrum, S1 of Z, is no longer estimable directly, because it's kind of folded back into the coarser scales. In particular, this band contaminates the estimate of all other bands L, and this is what aliasing looks like in the locally stationary wavelet situation. Okay, that's where it's coming back in. This was kind of the spectral stuff that we saw before, but the subsampling has caused this to fold back into all the other scales by just adding this constant to each scale. And of course, the constant depends on time. It can change over time here, m. The matrix changes a bit. The quantities are now every 2 because we're doing subsampling, not every 1. Okay, so in a way that would be quite nice. Yeah, if we did subsampling of an LSW process and then we observed in the spectrum of the subsample process that there was, for example, something that was the same size at each location, or at least it wasn't too far away from it, we might say, well, maybe there's some aliasing going on here. But the problem is white noise gives the same result. Yeah? So you can't, in this, distinguish between white noise or aliasing. However, you can detect a lack of white noise aliasing, which may or may not be useful, depending on what you think. So what do I mean by that? What I mean by that is, suppose you looked at your estimated spectrum for Y, and then you saw a scale where the value of the spectrum was nearly 0 there. Yeah? Well, that would mean that there can't be any white noise there, because you know if you have white noise, you have a constant added onto all scales. Okay? But it also means that you can't have any aliasing there, because if you had aliasing, you'd have a constant added on at each scale. So in the positive sense, if you have power at all scales, there might be some white noise there, or might be some aliasing there. That's maybe not that useful. However, if there is a 0 there at that location on that scale, then there is no white noise and there is no aliasing, which can be useful, which maybe just takes us on a little bit further than we were before. Here's an example. So this was a test locally stationary wavelet spectrum. This is the spectrum of the X, okay? And I've got power operating at the very finest scales here. And then at scale 3, I've got 2 blobs of power here and here. And what I'm going to do is take a realization from this time series, like I did before, subsample it once. So R is equal to 1, subsampling every second integer. And then what happens is the power in here, basically, this level disappears because we can't see it anymore. And this power here basically redistributes itself to all of the other scales. But here, there is no power. This is 0. So there'll be no aliasing going on here. Okay? But here, this power, there is some power here. When we subsample it, it'll disappear into the coarser scales here. So we're going to look at this at different locations. So there's a realization from that spectrum. You can probably just make out that here it goes a bit more mad in the middle compared to the 2 ends. And there's a dyadic subsampling of that realization. So that's at the integers. That's at every even integer. And if you're really perceptive, you'll notice that where it was really going mad here compared to here, it's actually going to be like white noise. Okay, that's what happens if you take the X spectrum and you sample it. That's the new spectrum. Okay, and you can indeed see, so 1's gone. You can indeed see some of the power's gone into 2, some of it will have added onto 3, and actually it's in all of these other levels, although it's more difficult to see because the scaling of this plot. But if you do rescaling to make each level come onto the same scale, onto the periodogram scale, you can really see that power redistributing itself into the coarser scales. Okay? And that's what we're going to look at. We're going to basically take a particular time and say, is there aliasing going on or white noise at any particular time location by taking a vector of values across here, and if all of the values are greater than 0, then it's going to be either white noise or aliasing. If there's a 0 somewhere, then there's no aliasing. You can see that's probably what's going to help us here, because here it's very close to 0. Okay, so we need a way of doing this, and our LSW thought experiment possibilities are as follows, because we've got this funny dual situation. You're just given a time series y of t. Okay? You may be in the business of suspecting it's aliasing, or you may be in the business of suspecting this is just a time series, sampled properly, and I think it's got a white noise component in it. And what question you ask depends on what you're really interested in. Okay. So one possibility for y of t is that it's a LSW from a subsampled LSW, like we've been talking about, or y of t could be equal to u of t plus eta t epsilon t, where u of t is locally stationary wavelet with no white noise component. So this u of t is locally stationary wavelet, specially designed to have a 0 for some scale. Yeah, it's kind of like the base model. And then I'm adding on some white noise with some slowly varying variance function, if you like. But the point is, it means that the way I've constructed it, y of t could be any LSW process, but it has a special representation. So u of t with this thing with a 0, or e to t epsilon t, which basically is saying that this is a LSW with no white noise component, add on a white noise component. So it's a way of figuring out what the white noise content of a process is. But the point is, it does mean that y could be any non-subsampled LSW. So this one is when we're in the world of thinking that there might be aliasing going on, and this one is just in the regular, we're not bothered about aliasing, we're just looking for white noise components. But both of these things imply that you have this kind of model in the spectral domain. So Sj of y is equal to Sj of u plus 2 to the minus j eta squared of z. And what we're going to try and do is basically see whether we have a white noise component, whether this bit is non-zero or not. Okay, so the null hypothesis that we're going to use is that there's no aliasing nor white noise at a particular time point z of naught. And that means, if that was the case, that at one of the scales of the y spectrum at some time point z of t, you'd have a 0. And the alternative is that all of the spectral content of y at time z0 for all scales is bigger than 0, and that turns into there's either a white noise component, that was defined by that model that you saw, or aliasing at z0. Now, of course, the issue here is that we don't know what Sj of y is. That's the model thing. We have to estimate it. Okay. So in estimating, I need to be aware of some things. If you can fall asleep for this slide if you want, if you're not already asleep. What we need to do is we need to look at a special number of wavelet scales, and I'm going to define JNC to be the largest integer less than this quantity here, and NC is just a set of all the scales that are less than JNC in size. So these are the finer up to some of the medium scales. It keeps away from the coarser scales, and they're called I call them the non-cone scales, because with wavelet transforms you have this what's called a wavelet cone of influence, which basically is to do with what edge effects that you have at the coarse levels of the wavelet transform. We want to stay away from those because they can affect our estimate. So the non-cone scales are the wavelet scales not adversely affected by edge effects. In separate work, Sanderson, Frizlovich, and Jones showed in a paper using some of these methods that the evolutionary wavelet spectrum estimates converge in probability using this condition here, and they choose a J star here to be 0.7 times log t. That's what they did there. And what's interesting here is this JNC is automatically less than this log 2 of t, so we can make use of their theory. If our time series is long enough, and what do I mean by long enough? Bigger than some quantity depending on the length of the wavelet filter. So that's good for our estimates and their distributional properties. What are we going to do for this test? Well, we're going to compute the raw wavelet periodogram, like I told you before, but just for the non-cone scale, staying away from these boundary effects. We're going to use, for this example, a simple running mean to the raw wavelet periodogram over k to get an estimate I hat of z0 at z0 using a manually chosen or a cross-validated bandwidth, again using ideas from Sanderson et al. I'm going to need the correction matrix that I talked about some while ago. I'm going to come up with a diagonal matrix, which is just 2, 4, 8, 16 up to 2 to the j and c. And I'm going to define this quantity q hat. What is q hat? Well, earlier I said that a minus 1 times I, that's our spectral estimate. So that's an estimate of S, the spectrum. And all I'm doing is just rescaling that, because for white noise for the spectrum, it goes down like half, quarter, eighth, and all I'm doing is renormalizing it to make all the values equal. So the question I have to ask as a hypothesis test is, at a given time, basically, are all the components, they'll all be on the same scale, and all I need to do is look to see if any of them are 0 or not. You can approximate Q hat by a Gaussian distribution. You can get hold of its estimated mean and estimated variance matrix, and from that we can estimate a multivariate confidence region for this quantity Q Z0, which is equal to lambda times S of Z0, and S of Z0 is a vector, and if any one of the S values is equal to 0, then that falls into our null hypothesis. So that since this is diagonal, that translates into basically looking to see whether any Q component is 0. So here's our confidence interval, standard multivariate confidence interval, chi-squared distributed quantile. And what we need to do is, it's a slightly strange hypothesis test, because what we need to do is find out whether there's any scale J, where this big confidence interval intersects the axis. Okay, that got me thinking for a while. Probably it's in the literature somewhere that I couldn't find, but the nearest I could find is that it's equivalent to finding the bounding box of a multivariate ellipsoid, for which there's some nice mathematics to do that. And if any of these scales, if the confidence region overlaps the axis, then you can accept H0, no aliasing, nor white noise, except for the time being. So let's see a simulation. The same spectrum that we had before, just power at scale 1 and 3, subsampling by every second integer. There's the spectrum again, and we're going to look at these time points here. And you can already guess what I'm going to try and show what happens. Here, there's no power at the finest scale, so when we subsample, nothing gets redistributed. So there isn't going to be any aliasing going on here. However, here, you'd expect there to be aliasing going on, because there's a lot of power here which needs to get redistributed to the other scales, and, well, probably here as well. And here, this is on the border of this power. What happens? Well, if you apply the test, 3 different sample sizes, 2 different wavelets to see what's going on. Here, this was this point 1, where we don't expect aliasing to happen, and indeed, seems very conservative, but it never detected aliasing. It detected it once, 1% of the time there. What about in the middle, where we expect there to be a lot of aliasing? Well, you can see here the power is very good for both of these. It's detected a lot of aliasing in those situations. Here, less so, but still quite good. And here, by the time you've got to a larger sample size, it's not really picking up any aliasing. And the reason why that 0.25 is slightly odd is because you look to see where it is. When you've only got 256 observations, the extent of that 0.25 in time series terms, in spatial terms, is quite large, because the sample size is not small. As the sample size grows, then the region that you're interested in, it narrows in, and so it's really only focusing on there. So for small sample sizes, it's picking up some of the aliasing that's going on there. Okay, Joe, just finally, I just thought I'd show a real data example. This was some high-resolution wind speed data, 1 hertz, somewhere in the Midwest, I think. Trend was removed by first differencing. There's evidence in this series of non-stationarity, as you'd might expect, both subjectively and objective tests. And there's a kind of question, which is a pseudo question: is 1 hertz enough for this time series? You can see the time series in gray behind here. And what I've done is I've picked a number of time points where I'm applying this test, the test of null hypothesis, no white noise component, or no aliasing, versus there is some. And here it rejects the test, and here it accepts the test. So here the test is saying that there is no aliasing or no white noise. And here there might be aliasing or there might be white noise. Yeah? Now the interesting question is, can we get any more information out of this plot? Well, if there was aliasing there, that suggests that there's frequency content at that point which is higher than the Nyquist frequency. And here, that's saying, actually, there is no frequency content higher than the Nyquist frequency. So it looks like the peak frequencies, the highest frequencies in this series have decreased going from there to there. All right? That's an idea. However, we can't really do any other analysis on there, any periodogram analysis, because if we believe there's aliasing going on there, doing a periodogram or a local periodogram on that region is going to be distorted because we think there might be aliasing there. So what we have to do is we can look, or what we can do, is we look at this region here and see what's happening to the frequency content there. Yeah. So evidence for aliasing white noise between those two times, 100 and 300. There's a guess that there might have been aliasing before, but not after. So let's apply a regular rolling local periodogram after time is equal to 300, and this is what you get. So there are 4 periodograms here with these windows of about 63, 64 width, and then we're moving them through times. The first one's 260 to 323, and then we're moving it, I think, 10 each time. And then looking at the peak frequency. So here, this is the peak frequency of the first one. At that frequency, this is the peak frequency of the second one. At that frequency, 3, 4. Okay. And then if you look at those times, they're the midpoints of the intervals, and look at the frequencies, there's definitely a decrease in the peak frequency. So that's an indicator, nothing more, not a proof, it's not a validation of any hypothesis, it's just interesting to see that power is maybe redistributing to lower frequencies. Somebody asked me, well, hang on a minute, how do you know which analysis wavelet to use? Yeah, usually you're using a locally stationary wavelet process. What do you use to analyze it? The answer is, in this case, unusually it doesn't matter. So if you have synthesis wavelets S for building the process, of course, which you don't know, then you choose to analyzing it using psi A. If you were doing spectral analysis or covariance analysis, it would matter which one you'd use. Okay, or at least but here, it doesn't. And the reason is because when you do the subsampling with the first wavelet, the effect of the aliasing is to generate white noise, which is independent of the wavelet. Whatever wavelet is used, it'll always come up with white noise. And when you're doing the analysis, it's looking for white noise. So this works because it goes wavelet through white noise back to wavelet again. So the method is robust to which wavelet you use for your analysis. So, remarkably, I finished on time. And really, just a few words in summary. If your time series is LSW, or you believe that, and there's a lot of things you have to believe in this talk, you can identify periods of aliasing or white noise components. But really, what you can identify is periods of not aliased. Can this be made to work for Fourier in the standard setup? And I think the answer is no. You can't get this to work using Fourier methods. And the reason is quite simple. If you look at a Fourier spectrum and you think about what happens just aliasing with the every other integer, you get this folding back. Well, if the spectrum on the higher frequency sides has quite a lot of zeros, a patch of zeros, and you fold back, then if that overlaps with a patch of zeros on the lower frequencies, you're going to get 0. You're not going to get any white noise. Yeah? I mean, generally speaking, when you mix the two, you'll get an overall shifting up of stuff, and you may get power you didn't get it before, but you cannot guarantee that you'll get white noise coming out of it in the same way as you do here. So it is a special setup. It's not general, but it's an interesting little wrinkle. Okay, thank you.